Hi, it's time for another math easy solution. To discuss further into conic sections and look further into ellipses. Now we'll go over example 3 of the example series, and now we'll prove a reflective property of ellipses, which makes it actually very useful in real-world applications. Yeah, so before I get to the example, so basically interesting property of ellipses, like parabolas, ellipses have an interesting reflection property that has practical consequences. If a source of light or sound is placed at one focus of a surface with elliptical cross sections, then all the light or sound is reflected off the surface to the other focus, as I will show in the following example. And this principle is used in lithotripsy, or lithotripsy, I'm not sure how to pronounce it, a treatment for kidney stones. A reflector with elliptical cross-section is placed in such a way that the kidney stone is at one focus, and then high-intensity sound waves generated at the other focus are reflected to the stone and destroyed without damaging surrounding tissue. The patient is spared the trauma of surgery and recovers within a few days. I'll go over lithotripsy and whispering galleries as well in a later video, so hashtag stay tuned for that. I just wanted to bring that up right now, just to bring to your attention that ellipses are pretty useful in real-world applications. So now let's look at example, this one right here, and prove that reflective property of ellipses. So let P of x1, y1 basically be a point on an ellipse. I had a hyperbola for some reason there. So on the ellipse, x squared over a squared plus y squared over b squared equals 1. That's just a standard equation of an ellipse with foci f1 and f2. Remember, plural. Foci is just plural for focus. And let alpha and beta be the angles between lines pf1 and pf2. And pf1, pf2, and the ellipse as in the figure right here. So there's the point, there's our ellipse right here, and this is the angle, right here, f1 to p. Now you have an angle in between on this tangent line like that, or it's on the ellipse, but as you get closer to the tangent line, you get basically this angle across there. That's alpha, and there's beta from f2 to p2, and there's the tangent line across there, and that's the angle in between beta. So now we're asked to prove that alpha equals beta. So if you had one focus and you shoot it at here, these angles are the exact same, and then it just reflects right back to that focus, which is quite interesting. So this explains how whispering galleries and lithotripsy work. And again, I'll go over whispering galleries in later videos, so stay tuned. So sound coming from one focus is reflected and passes through the other focus. Yeah, so if you have sound, if you have a ceiling, for example, and it's shaped in elliptical fashion, you could just talk from here, bounces here, and it goes there, and you can overhear other people. So yeah, more on this later. So now I'm also given a hint. My calculus book gives a hint, says use the formula in my earlier video, which I went over on the angle between two lines formula, to show that tan alpha equals to tan beta. So we'll have to apply that formula twice, and then we can finally prove that they're equal, the angles. So let's go ahead and try to solve this or prove this. So first of all, recall that equation of the two lines, or the angle between lines formula. I just quickly added 2. So angle between two lines formula in my earlier video, and basically right here, if you have, I'll call this line L1, and this has a slope of M1, 1 like that. So then let's say you have another line here, this is L2, and it has a slope M2 like that. Now you have an angle in between here, alpha, like that. And then I proved in that earlier video that tan of alpha is equal to, well, M2 minus M1, 1 plus M1, M2 like that. Where these are, again, just the slopes of these two lines. And also I want to make a note. Basically, if you interchanging M1 and M2, all it does is, well, you'll just get a, you just switch the sign, switch to plus or minus of tan alpha like that. Yeah, so all we'll do is just have it negative or positive, so it doesn't really change anything. Yeah, so we shouldn't be too worried about which one are we subtracting from, because if it's m1 minus m2, and then there'll be a negative sign there, but then this gets flipped as well, and this will make more sense to get through in this video. So let's just move forward. Yeah, so let's draw this ellipse, and then we'll do a tan alpha first, and using the formula, then afterwards we'll do a tan beta, and then I'll show that they're actually both equal when we apply that formula. So we have this. Let's just draw this again and set that formula up, and I'll just write here as tan alpha here. So what we'll do is, let's say, draw the XY axis like that. Let's say we have an ellipse like this. Well, that was a very good drawing for my first try. Usually I have much more messy drawings. Yeah, so we have this right here, and let's just write this is our ellipse, x squared over a squared plus y squared over b squared equals to 1. And now let's say we have our foci right here. This is our f1, this is our f2, and remember that these are just separated by, well, c, and this is c, the distance. Yeah, we're at this exact point. That's a negative c. This one is at plus c, but the distance absolute values is just c. Let's put absolute value like that. Or actually, I'll remove those absolute values. Yeah, because I'll just assume c is positive as always. So anyways, now we'll just do is, let's say we have a point here, and this point is p, and again this is at right here. I'll write this as x1, and then this has a y value there, y1. Yeah, and here I quickly just move things around, move the plus c away from there, just to indicate on, if I have it above this axis, just make it as a distance, and then here's the point 0 and c, actually it's the other way around, this is c0. Yeah, that other one would be for a vertical ellipse, so like that, and that's negative c0. And now what we'll do next is, well, we need to determine that tan alpha to make it look like this formula so we could apply it. So tan alpha, this is the one that's going to make it from f1 to p, and then with the tangent line across there. So what I'm going to do is, I'm going to draw this from here to here, and then I'm going to just extend this, keep going on, and likewise from there's a tangent line across there, and I'm going to keep going downwards like that. So now we have this angle right here. Yeah, this is just our alpha, and this is our, well, there's our alpha as well. Now what I'm going to do is I'm going to call this L1, just because my calculus books use it that way. And yeah, so that's L1. Let's say this line has a slope m1, 1 like that, just indicating rise over run. And then we'll call this line L2, and this is going to be our m2, 1 like that. Now we can solve these slopes. Well, this slope is at this point at p. This is just a tangent line, so we could use the derivative of y, and this one we could use the rise over run of this triangle. But no, this c was from this distance up to there. So what I'm gonna do is from here to here is x1, and then just from here to here is c, like that. So basically we have x1 there. This is y1, so we could determine that just by this triangle. Let's just rise over run here. So x1 plus c there is the run, and then y1 is the rise. Yeah, so thus what we have is, well, tan of alpha equals to m2, m2 minus m1, just from the above formula, 1 plus m1, m2, like that. Where m1, that's just the slope of, well, the tangent line. So m1 equals slope of tangent. This is the slope of the tangent at the point at right here x1, y1, or the point P, x1, y1. So then if we just plug in our formula for an ellipse, we have x squared over a squared plus y squared over b squared equals 1. Now what we'll do is apply implicit differentiation. So we have this. So what we'll do is we'll d over dx on both sides like that. So we're not changing anything. D over dx like that. So what we'll end up having is, well, this is going to be right here 2x over a squared. That's the derivative of x squared is 2x. And then this one here, we're going to get a 2y, and then the derivative of y is this y prime using chain rule over this b squared, and this one is just a constant, derivative is a 0. So now we have that. We could cancel the 2's, divide 2's both sides, move this over to that side. What we get is a y over b squared y squared equals to a negative x over a squared, like that. So now what we'll do is, well, multiply both sides by b, so move this over there, and the y, we move it at the bottom. So what we get is a y prime equals to a negative b squared over a squared x over y, like that, there, and then, so then what we have is now at P, at the point P, we have, point P, which is again x1, y1, like that. We can just plug in those values. So then we get a y prime equals to negative b squared over a squared x1, y1, like that. And I'll just circle this one because we'll be using this. Yeah, using that in our formula. And then this is actually, just equal to m1, like that. Remember, that's the slope of the tangent line over there. So m1 is the slope of that tangent line. So that is what our m1 value is, negative b squared over a squared times by x1 over y1. So now what we have to do is solve for, well, m1, or m2, that's just going to be the rise over run. That's just, we already have a triangle there, y1 over c plus x1. So like that. So we have a, let's put it here, m1, actually m2. So m1 we already solved. m1 equals to rise over run, which equals to y1 over now we have, this is x1 plus c. Yeah, so this is our value. So thus what we end up having is, thus we have tan alpha equals to, again, m2 minus m1, just put it there. So refresher, m1 times m2, which equals to m1 is over there. M2 is right here. So y1 plus, divided by x1 plus c minus, now we minus this is going to be, well, positive because it's already a negative, b squared over a squared x1 y1, like that. And then we divide this all by 1 plus m1 times it by there. So that's a negative, so this becomes a negative there. B squared over a squared x1 over y1 times it by m2, which is y1 over x1 plus c, like that. So now what I'm going to do here is, well, I'm going to multiply by the denominator on this side. This is a squared y1 x1 plus c. This one we have a x1 plus c. There's an a squared y1. So you want to get rid of all these denominators. So what I'll do is multiply top and bottom by the full one. So a squared y1 times by x1 plus c, and divided by, and then divided by here, like that, a squared y1 x1 plus c, like that. So we don't change anything, and then when we do that, what we end up having is this equals 2, and this is going to be a lot of algebra. So the x1 plus c cancels with that, so we're left with a y1 a squared y1, and now this a squared y1 cancels with these two, so now we're just left with x1 plus c. So we have plus b squared x1 times x1 plus c. Divide that by, put that over there. This divided by, now this bottom one, this whole thing cancels, that's the same as this, and then we'll just left with, well, this is 1 times that. It's going to be a squared y1 x1 plus c, and then subtracted by, and then that's just all cancels. So b squared x1 y1. And now what we could do is just, well, multiply that out and see what we get. So we get a y1 on the top, a squared, this y1 there, that's just y1 squared. Actually I'll put the a squared first. So we have an a squared y1 squared, like that, plus b squared x1 squared, because we're multiplying by itself. Then we have a plus b squared c x1, like that. And then this is all divided by, now we have this part here, a squared, now they have y1 x1, or y1 x1, like that, plus this multiplied inside, a squared y1, and then c, like that. And then all of a sudden, you just subtract it by the last part, minus b squared x1 y1. And now notice what we have. Well, first we could simplify this part here. We could just factor this out. Yeah, this x1, y1, and this x1, y1 there, so that we have an a squared minus b squared. And the reason we want to do that is, well, let's write that down. A squared a squared y1 squared plus b squared. So again, it's just a lot of tedious algebra right here, but it's pretty fun if you just follow through. So now what we have is we factor that part out, so we have an a squared minus b squared like this, and then we have a y1 x1, and then plus a squared y1 c. Or actually, I'll just write the x1 first, just because my calculus book does it. It seems a bit better like that. So yeah, x1, y1 like that. And again, the reason is, recall from by definition, or actually basically from instead of. So from ellipse derivation video that I made earlier, ellipse derivation, what we did was we defined defined b squared equals to c squared minus, actually the other way around, a squared minus c squared, like that. So if that's the case, this is what we defined it as. Then we can just rearrange this and move this on this side, move the c on that side. So what we end up getting is a c squared equals to, well, an a squared minus b squared, like that. And that is this part right here. That's just c squared. And also, so note from our equation of an ellipse, so we have, note that x squared over a squared plus y squared over b squared equals to 1. What we'll do is, if we multiply both sides by a squared b squared, we can get this part right here. And the way we do that, well, we'll just multiply both sides by a squared b squared, like that. What we end up having is the a squared cancels with this. We left with b squared x squared plus right here. This is, now the b squared cancels, we're left with a squared y squared equals to now a squared b squared, like that. So this means we have this part here. Doesn't matter what the x and y values are. What we end up having is b squared times x squared plus a squared times y squared equals to a squared times b squared. So that means this one, even if it's y1, x1, doesn't matter. This is just going to be equal to a constant, which is a squared b squared, like that. So we could put this all together and finally get, we can get thus, now we'll just put that in. So we have tan alpha equals to, and let's scroll back up. So now we have an a squared plus b squared, a squared b squared, so that simplifies to that, plus right here now we have a b squared c x1, b squared c x1. And then we divide this all out by, well, this is now c squared x1 y1, and then we have an a squared y1 c. So we have a c squared x1 y1, and then plus a squared y1 c, a squared y1 c. And now what we'll do is, we'll notice we can factor out in the top the top part, we can factor out a b. So we can factor the b squared on the top. This equals to, well, b squared, and now we have an a squared plus c x1, like that. And in the bottom part, what we could do is, well, we can factor out the y1 and c. There's a y1, there's also a c there, so y1c, like that. So what we'll do is a y1c over, I just factor out, now we have a c by itself, c x1 plus now a b, this is now going to be an a squared, like that. Actually, everything is gone but the a squared there. This is the same thing as the top part. So this cancels with this. We're left with a b squared over a y1 c, like that. So this is our tan alpha, like that. Put it over here, and there is our answer there. So that's this value. I'm just going to rearrange, just put c y1 in front, like that. So now the next one we got to solve is, well, tan of beta, as the hint from my calculus book. saying do that, then you'll see that they're both equal. So to find the tan beta, what we'll do is, well, just go back over here, and now I'm just gonna move this y1 over here and write that in blue. And now we're gonna draw it from here. This is our f2, not our f1. Yeah, I just made a mistake there. So now we have it from here to here. Yeah, this line, I'm going to draw this in blue, extending to there, but then it keeps going on and on, upwards. Draw this better again. Yeah, it keeps going on like that. Now we have this angle, this is our beta, like this, and now we have a beta again here. This is with this tangent line. Yeah, so now we can apply that same formula. We know M1. We'll call this line right here L3, and this has a slope as a M right here, M3, and this is 1. And we could use the slope, well, this one right here, this is just a triangle there. This distance of absolute values is going to be x1 minus c, like that. And we have the y values there, the run y1. Reason I'm doing absolute value, because this this x1 is on the left side, but remember, if you had a point on here, x1 is going to be different, and it's just going to be a different sign. So just put that like that instead of writing c1 minus x1, because again, wherever the x1 is, the values will change, etc. So I'm just putting that as default. So that means we can solve for our m3 right there. Yeah, where m3, again, it just rise over run, because we have the triangle, and then this just equals 2. Well, just the rise is going to be y1 over x1 minus c. It's just a difference there. And again, it doesn't matter if we switch these around, use absolute value or the y1, because it's already descending, you can put a negative there, but all that will change is the signs will change and your end result. If you get them mixed up, it doesn't matter much. So just jump right in. What we do now is apply the tan beta. This equals to, well, my calculus book goes with m1 minus m3, but again, it doesn't matter. You'll just have it different signs. This is going to be plus 1 m3, as long as there's just a difference there, and then you add the two slopes like that. Because remember, if you have a different sign there, you could already see visually that, well, they're just assumed they're the same positives like that, because you could just see it like that. So the signs don't change much. So yeah, don't worry if you have it m3 minus m1, doesn't matter. Yeah, so that's what my calculus book does. So now if we subtract this, so we know m1 from above, let's scroll all the way back. m1 is negative b squared over a squared x1 y1, like that. So equals to negative b squared over a squared x1 over y1. Then we subtract it by m3, which is above there, y1 over x1 minus c. And then we divide this all by, well, 1 plus, and now we have this, the m1, that's going to be negative, so let's put a negative there. Yeah, so negative b squared over a squared x1 y1, and then times it by the m3, that's just y1 over x1 minus c. Yeah, like that. And now notice here the denominator of this one is a squared y1 and then times x1 minus c. And this one we have an a squared y1, there we have an x1 minus c. So we'll do the same thing as above. We'll multiply the top and bottom by the same, so we're not changing anything. A squared y1 x1 minus c over a squared y1 x1 minus c. So when we do that, what we end up getting is a negative, b squared x1, and then now a squared y1 cancels, we're just left with x1 minus c, like that. And then we subtract here the y1, now we have, this is going to be a squared y1 times y1, there it is, that becomes squared, so y1 squared. Now the x1 minus c is gone, because I just canceled with that part there, so we're left with that. And then we multiply this one inside there, the whole bottom part cancels there, the 1 times that is just that value. A squared y1 x1 minus c, and then minus, now that all cancels, minus b squared x1 y1. And now we'll just multiply this all out, and we're going to get pretty much the same steps or method as we did for tan alpha. So now what we're going to get, multiply that out, we get a negative b squared x1 squared, negative b squared becomes positive b squared cx1, and then we have a negative a squared y1 squared over there. Now divide this all out. This is, divided by the bottom here. A squared y1 x1 minus, multiply that out, a squared c y1, y1, and then minus that part there, b squared x1 y1. So same as above, what we'll have here, now we have a negative, this a squared y1 squared, negative b squared. We'll do is take out the negative, and we're left with here on this side b squared x1 squared plus, we just do that, factor out the negative on these two only, plus a squared y1 squared. Then we just have this part b squared c x1, because again the reason is this just equals to a squared b squared as shown above in this little note there. So b squared x squared plus a squared y squared equals just a squared b squared, and that's exactly what we have there. Divide this all out. You divide this out by, and then we're gonna factor out the c y1. Actually do that after, so we'll, yeah, that was just jumping the gun. So now we have a squared and then negative b squared, so we'll factor this y1 x1, this x1 y1, same thing. So what we'll do is now we'll have an a squared minus a b squared, then we have x1 y1 like that, minus this part a squared c y1, and again we do this one equals to, well, just c squared right there as showed above, and that's just our, again, our a squared minus our b squared like that. So now that we have all that, put it all together, we have a negative a squared b squared plus b squared c x1 over c squared x1 y1 like this, minus a squared c y1, and now what we'll do is factor out the b squared on the top, so we get a b squared, and then we have a negative a squared plus c x1 like that, all over. Now what we have on the bottom here, we'll factor out the c y1, and then as you'll see, this one will have remaining as just one c x1, and then we have a negative a squared, and that's exactly the same thing there. Just rearrange differently. So then we have, that's b squared over c1, so we have tan alpha equals to b squared over c y1, which, as I showed above, let's go back up to that value, tan alpha equals to b squared over c y1, b squared over c y1, this equals to tan alpha, and what do you know, that's quite an amazing result. So thus we have tan alpha, or tan alpha equals to tan beta. In other words, we have these are both equal, so we have alpha equals to beta like that, and we've just proven the reflective property. Quite amazing like that. Yeah, so hopefully you followed along. It's pretty intensive example slash derivation slash interesting property of ellipses. So anyways, that is all for today. If you learned, and like always, you can like always, you can download these exact notes in the link below. In the next video, I'll go over some applications of ellipses, such as the lithotripsy and whispering galleries, etc. And also, yeah, you could also view these exact notes in article format on steemit.com, so check it out. I'll upload that shortly after I upload this video. Anyways, thanks for watching, and stay tuned for another Math